Hi, I'm Steve Bible. I'm going to give a talk here about SUITSat 2 to ARISSat 1 and give you basically a SUITSat ARISSat update. And you'll probably wonder what is ARISSat. So I'm pretty sure this is going to be quite new to a lot of you. For those of you that were here last year, I gave an update on SUITSat 2. And this is basically what's transpired over the past year. The SUITSat project's gone through a lot of different iterations, so this is, of course, the latest, and so, of course, subject to change, as they say. Now, SUITSat 2, for those of you familiar with SUITSat 1, of course, now I'm kind of dependent upon the fact that you know about all of these other projects. SUITSat 1, for example, which we flew back in 2003, was a very simple transponder, transmitted voice messages to the ground on 2 meters, and the goal was for it to be very easy to receive. Turned out the antenna didn't work out as well as we hoped, and it took a little bit more antenna on the ground station in order to pick it up. But the neat thing about the internet, of course, is a lot of people recorded what they received, and then that got posted up on the internet. And then for those took the challenge, dusted off a lot of those 2-meter beams and got those up and pointed them at the sky. So there was a lot of excitement with that, and then it was a lot of fun to follow a lot of the different recordings literally around the world that hams around the world were listening to SUITSat 1. So with the success of SUITSat 1, we wanted to work on SUITSat 2. And who are we? Well, we is a bunch of volunteers, engineers, hams, whatever. Bill Reed here, up in front, say hello, Bill. Bill here last year wanted to get involved. So, boy, did you get involved this year?
I'm afraid so.
Yeah, I'm afraid so. So be careful what you volunteer for, okay? It's turned out to be quite a big project because, as you can see here, the objectives, we wanted to make it a much more capable payload. And of course, when you make something more capable, it's more complicated. And complication, now you got to communicate well, you got to document well, and in a volunteer project, that's not always the case. So what happened is SUITSat lost its suit. And how did that happen? Well, many of you know that on the International Space Station now is now occupied by 6 astronauts and cosmonauts. So now, get this, space is at a premium. R. And so they needed to clear out some of the space inside the International Space Station. And now, the Russian philosophy of their spacesuits is that they dispose of them, and we do mean dispose, as in get rid of them, they burn up in the atmosphere type of disposing after 5 years or 12 wearings, whichever comes first. And so suit number 27 had our name on it, but we didn't have the equipment ready to deliver, to put inside the suit. Then the manning of the International Space Station grew from 2 to 6, and of course then they had to get rid of it in order to make more room. Now the way they get rid of things is the Progress, which is an unmanned space capsule, is kind of what is the UPS truck of sorts that goes up and takes all of the supplies up to the space station. It docks, then they unload it, and now this becomes a space sort of dumpster, where now it's empty, so now all of the trash goes into it, and they leave the Progress docked until the next Progress is ready to come up. And about a week before they launch the next Progress, then they let it go, and it comes down and burns up. So it's the incinerator of the trash disposal. So basically, they had to dispose of the suit. We lost the suit. So SUITSat is now SUITLESSat. So then we had all sorts of discussion about how we were going to name this project. So certain ideas like SUITLESSat, The other one I liked a lot was ARRSat. So we were kidding around as to what kinds of names. Now, we still have a way of getting a payload up. That's the upmass in January. So basically what was transpired is ARISSat, and of course ARIS stands for Amateur Radio on the International Space Station. So now we've enlisted the help of a mechanical engineer who's working on this particular space frame. So this is kind of what's on the plan and what's being drafted and what's going to be built. And you'll take a look at this. It's, of course, a space frame, but notice we have solar panels. There'll be 6 solar panels for the 6 sides, the 4 around the side, 1 on the top, 1 on the bottom. And we're going to reuse a lot of the equipment that we built for SuitSat. For example, you may recognize the switch box that would previously went on the helmet. The antennas will be a little bit different. And then this thing here is an experiment that the Kursk University in Russia want to fly on SuitSat. Now this is the block diagram for SuitSat 2. The idea is that there would be a box on the inside that each of these is printed circuit boards that stack on top of one another, solar panels that we were planning to Velcro around the legs of the suit, and then the transmitter receiver, the cameras, and the antenna, all of this would be, and the switch box would be mounted on the helmet. And then provisions here for putting up to 4 experiments, and the battery. The battery, of course, being the battery that used to be inside the suit. So that would be disposed of and provided for us. Now, if you were at Dayton, this was the SuitSat 2 demo, and it was actually up and running. So now this is not a space helmet, but kind of gives you the idea. So here's the switch box. This silver box here is the transmitter receiver. The blue box has the cameras, the antennas on top of it. And this is the box with a stack, what we call the stack of electronics. And then, of course, the cables that link everything together. So this is actually up and running. Now, here's the capabilities of it. Basically, we want to do 2 meters down, 70 centimeters up. We want to be able to have a transponder. Everybody will listen on 2 meters, hopefully talk through it, and also the video, transmitting video down. Now here's what's happening. Now we've taken basically that same equipment but kind of repurposed it. It's basically taking that earlier block diagram and just shifting it around, but what we're trying to do is the original equipment, the boxes and the electronics, we're not trying to change it too significantly. Now of course, the solar panels now go around the box, and that'll show you another change that we'll make to the power system. Now, the solar panels are actually high-efficiency panels. These are space-rated panels that were basically donated to the project from NASA. We have 8 of these, so naturally 6 of them will fly, and then we'll have 2 as spares. And here's how we test them. We find somebody with a pickup truck in the Arizona desert, and then we go out in the parking lot. And what we're doing here is you'll see the solar panel, and then you'll see a couple of meters, and then of course what we're doing here is testing what's called the max solar power point converter, which was designed by John Charez. John's the fellow right here. Next to him is Joe, and this is one of our interns at work, Tim Moffitt. And we're testing it out in the sun. And I forget, this was like February, so you could see the short sleeves. It was kind of a nice warm February. And of course, this is in Arizona. Now, what I'm going to do now, I've got the box basically circled here because I'm going to show you more detail of the box. So this is what we call the stack. The bottom larger one is the interconnect box, or the ICB, allowing all of the boards to be able to connect up to it. And then the idea is that all of the connectors that need to go elsewhere outside of the box then connect up through here. Now, the ICB is going to be redesigned because now the box, we had all of the connectors on the outside edge. Now we're going to take those connectors and put them on the lid because it's going to be bolted to the space frame differently than just being put inside the suit. Next up is the power supply board, and then up from that is the internal housekeeping unit, and then on top is the software-defined transponder. Now, what's interesting about a lot of this electronics is, of course, a lot of the high-altitude balloon people are interested. We've talked with Bill and also Doug Loffmiller in Texas. So what we hope to do is also provide this type of equipment, though it doesn't need to be this extensive in the solar panels, but at least the communications payload could make for a very good electronics package for the balloons. And what we need to do, though, is take what we've learned here, get it down into a smaller size so we can stay below that 12-pound limit. And I'm pretty sure we can do that. So first off is to get this working and get this shipped. So here's what originally was to be done. You can see the ICB down in the bottom of the box, and this is a Hammond box, and the idea is that then the outsides of it would be machined. So now what's is different is the ICB will now go on the lid of the box, and all of the connectors will come up through the lid. But the rest of the boards will be plugged in like we originally intended it. With the exception of the power supply unit, each of these, you can see that there's 6 of these circuits. They're pretty much identical. They're rubber stamped on here. These are the max solar power point converters. The idea now is we're going to make these on their own separate circuit boards and place these on the back of each of the solar panels, and then feed that back to the power supply board, which also has a microcontroller that's giving communications back and forth to each of these and checking their status and collecting telemetry for them. So this board changes in the fact that we will take the existing circuitry and break it up and then redeploy it. But the circuitry as it is right now would stay pretty much the same. In other words, we're not trying to do a lot of new circuitry changes, but we are trying to take what we have and then repackage it, only because the space frame changed on us. So now the internal housekeeping unit, this is the block diagram. I've showed this to you in the past. The main processor is actually a microchip PIC32. The video digitizer, and I'll show you a little bit more about that here in a moment. The idea here hooks up to 4 cameras, does the digitization, and then the microcontroller then retrieves that and then encodes it into a slow scan TV format and then transmit it down on an FM channel. Then over here, the SDX is another board that plugs into it, and here's your experiments. So now here's what it looked like at Dayton. This was the box, and pretty much what we were hoping to put it in and deliver it for SuitSat. You can see the connectors on the outside. These 4 connectors are for the experiments. Then this connector here goes up to the helmet. And then on the other side, this big connector is a 50-pin connector. This goes up to the helmet. This is one of the solar panel power connectors here. And then this connector you can't see on the back side here is for the battery. It's one of the big round type of battery connectors. And you'll see a lot of LEDs lit up in here. Of course, in space, you can't really see LEDs, but the idea would be we use this a lot for debugging. When you design and develop things, you try to put a lot of little things in there that help you do the debugging, like a serial port, LEDs, ports for putting logic analyzers on there. So naturally, for the boards that go into space, we'll just remove those LEDs. We just won't populate them. Now, here's how the whole SuitSat 2 system goes together. and how we would have the SDX, which is basically a software-defined transponder, meaning we're using the QSD, QSE type of architecture, and it's a 10.7 IF all the way up to the transmitter and receiver, which we intended that to be up on the helmet as close to the antenna as possible, where the SDX would have been inside the body of the suit, and then a 10.7 IF cable, coax cable, running between that box inside the body, out the arm, and then up to the helmet. So we didn't want to have a lot of attenuation there, so we chose the 10.7 IF. And then the 2 meters and the 440 would be up on the helmet, and then it would be an incredibly short feed to the antenna. And that way, that would reduce any types of problems or attenuation when it comes to the 440 and the 145. And then here's the band plan. This is the band plan that we got filed. On the 2-meter downlink, which is blue here on the top, you can see down on this portion we have FM. This portion, which we label transponder, would be for your sideband up and down. You would uplink in the 70 centimeter portion, and then it would downlink in the transponder section in the 2-meter band. We would also have a CWID, and we're also putting a 400 baud BPSK telemetry downlink, basically repurposing the 400 baud BPSK, which was Oscar 13's and Oscar 40's telemetry. So that software that runs on a PC that decodes it will also decode this. So that way you already have, that software is already written. It's not something we have to rewrite. So now we just include that modulation and then put the telemetry on that. And we have a volunteer that's basically writing the PC side of that that's going to be able to display all of the telemetry aspects to SUITSAT for you. So now we're working on, we'll have a voice ID, so very much like SUITSAT 1, where we're going to have the greetings from space from the various member countries to the International Space Station, and also the greetings from Russia. That's what the voice greeting. The voice ID will say this is SUITSAT and the call sign. The slow scan TV is going to be in a robot 36. Why? Because we wanted it as short as possible. So your robots are the ones that transmit the shortest amount of time. And robot 36 was our choice because in a pass of a satellite in very low Earth orbit, at the best, even if it just goes over the top of you, is 10 minutes. And that is not the norm. So most of the times the satellite's going to pass over the horizon where you're going to have, say, 5 minutes or less. So we wanted to have the slow scan as short as possible. The trade-off is it's not as great a resolution. So it's only a few pixels. And then we wanted to be able to put packet, our good old-fashioned AX25 packet, sorry about that, and we're kind of running behind on getting this implemented. CWID with commemorative call signs, so basically you can copy the CW and copy all of the different call signs. We're planning to put on there to commemorate a lot of the people who are involved in SUITSAT and others to be decided. The BPSK, the experiment telemetry, this way we're going to try to work with the old AO40 BPSK, and also Phil Karn has been working on a more robust forward error correcting scheme that we want to experiment with. And then the transponder, as I mentioned. Now, as I mentioned at Dayton, it is up and running. So here is basically the display from an SDR-IQ, and it's displaying the transmitted signal. The neat thing about using SDR-IQ is you can see all of the different signals that are being transmitted at once. And then here it is what it looks like on a spectrum analyzer. We basically put the spectrum analyzer into max hold, and you're able to see the CW and then the BPSK. I think this over here being FM, this is your wider. I'm sorry, I don't remember which is which, but we were all very excited that day, weren't we, Bill, when we saw this on the spectrum analyzer. We were like, wow, it really does work. So we were all very jubilant. So the idea about the video, and the reason why we have 4 cameras, now on the suit, we wanted it to point 4 different directions. And we're going to try to get at least 2 on the ARISSat. Now, what are we going to do if the picture is not any good? We're going to put an algorithm in there that's going to take a look at the pixels, and if they're all the same color, then we're going to deem that as kind of a poor picture, go back and take another picture. So we want to see some variety in the pixels before we attempt to transmit it down. Each pass of the satellite is like every 90 minutes is an orbit of the International Space Station. And it would be the same for ARISSat when it first gets launched, but as it gets closer and closer to Earth, that's going to get faster and faster. So you, to be able to listen to it, you're going to have to get quicker and quicker and quicker. Thus, the reason why we're using Robot 36. And given that we're going to be transmitting, even if we're over the ocean, we're trying to make sure that when we set up and transmit a picture, we've got a good picture, and then we will continue to broadcast that picture for several hours, for example, until somebody on Earth can capture it, and then, of course, share that on the internet. So here is a picture of the Owens twins. You're supposed to laugh at that. That's father and son, the Garretts. Owen Garrett and Richard Garrett, who were at Dayton, which was a lot of fun to listen to Richard. And so we took a photo of them and put it out in front of the camera so you can see that's probably Jerry's hand there. Jerry Zdenek is the one who programmed the video. So you see it actually works, so we were really excited about that. Now what's interesting is we're taking a camera that puts NTSC out. It's captured by an NTSC chip, using an FPGA to store that into a static RAM, and then a microcontroller reads out of the static RAM the locations and then transfers that to slow scan TV. And then somebody discovers, just like Bill showed you in the earlier talk, here's a camera with a serial port output, and go, duh. Wow, why didn't we just use that camera? But, you know, being engineers, this was a lot more fun to do. So you kind of have to chuckle at yourself because we were really proud to get this up and running, and we're all patting Jerry on the back, and then all of a sudden discover these other cameras that would make it infinitely easier, because now you take this camera that basically outputs a JPEG in digital format, and you don't even have to turn it into slow scan tones. Just transmit it down in a digital stream. So you got to think out of the box sometimes. But when you're working to develop something that everybody can get cheaply and easy, like slow scan TV software for your PC, yeah, you're kind of designing toward that. Here, now you recognize this fellow over in the corner here? Look, he's even got the same shirt on. I hope you washed that, Bill.
Not yet.
Not yet. Okay, so this is May, this is September, go figure. Now, here you're showing you've got a radio set up, and we've got several computers here displaying the received signal from SuitSat, the earlier picture that you saw. This was set up at Dayton, being demonstrated at Dayton. Now, what we're taking from Dayton to present is the Dayton demo, as we call it. We had a certain amount of functionality, that being the FM being transmitted, the CW being transmitted, the BPSK being transmitted, the slow scan cameras being taken, and that was it. Oh, and then we had the FM, which was doing the recorded voices, so we had that going. So what we need to do is we still got to get all of the IHU functionality working, talking back and forth to the SDX. We need to get the telemetry stream collected and then transmitted. And then we need to be able to talk to and control the max solar power point converters and the PSU. So really, from a communications aspect, we had this up and running, but from a complete satellite perspective, what you're seeing there on the table is about 50% done, and we still have a lot more to do. So that's what we've been busy since May till now working on. And the experiment that's going to be run is one that Kursk University has put together. And this is bullet points of, if you wanted to build your experiment, this is the interface that you would design to. The idea is that we would come up with a SUITSAT type of electronics with this experiment interface, and we could, once we've proven the communications hardware, then we would reproduce this over and over again, and what would change from satellite to satellite would be the experiments. So we came up with an experiment protocol, and we created basically development kits of sorts, which we also developed a simulator, which you could plug in your experiment to the simulator, and it would be like talking to the IHU. Now, for now, we only have the one experiment from Kursk University. And this is it, Kursk State Technical University, and what they want to do is basically measure vacuum. And they want to see, as the satellite's going through the lock and then it's going to be deployed, what is the rate of change of vacuum when they do that. They're pretty excited to be able to measure that. So this is what we hope to see. You just take your satellite and post it, Photoshop, and then you declare it launched. But I mean, this is, okay, so what this is an artist's conception of ARISSat in space. How do you like that? It's a low rent. Yeah, it's a low rent. We didn't have lots of money to pay a graphic artist to do that, yeah. Now, Bill, did I miss anything? Something else to mention on that? Okay, so take some questions.
The question I have, basically the BPSK telemetry, are you releasing software for people to help with collecting that?
Oh, yeah. What we'll do is we have a volunteer that's writing the PC program that will decode it and display the telemetry, yes.
Is it multi-platform?
He's writing it in Windows. Is it Douglas? He's writing it in Windows, isn't he? Yeah, I believe it's Windows for now. But is he releasing the code to that? I mean, most of the stuff we're doing is open source, open hardware, so all it does is take an intrepid volunteer to port it over to other platforms. Hint, hint, hint. Over here?
Well, Steve, I've got a couple of questions. One, I guess, didn't hear much in terms of the actual launch process.
Oh, okay. That's what I forgot. Okay, the launch. What we do is we have an up mass, they call it, in January. And what we're attempting to do, and we're like trying to finish everything up, we've got to get everything integrated, put together, and shipped out of the States like the weekend before Thanksgiving. So we're all just, I should be home right now working on this instead of here.
We're glad you're here, Steve.
Yeah, thank you very much. Bill should be at home too, but we decided we would be here. So what we're doing is we're putting in a little overtime, trying to get this finished, finalized up. We still got a lot of technical hurdles because the whole satellite concept, this is like the fourth change. And so getting over this change from SUITSAT-less sat to ARISSat, there's quite a few changes. So we're trying to as smoothly as we can. It's a big project and it's very complicated and trying to keep it coordinated and keep it moving. So basically our drop dead is we've got to deliver 2 of these things before Thanksgiving. Then it'll go to Russia, they'll do their testing, then put it on a progress in January with hopefully a launch in springtime 2010. So that's what we're hoping. If we miss the Thanksgiving date, then it's all off. We will have to search for another launch opportunity. But this is open to us right now, and we've got to meet this window. Does that answer your question?
Well, part way. I also wondered about actual, I mean, well, what do? They get it up to the space station, and then some guy decides, hey, I'm going to go out for a spacewalk, and just kind of flings it a little bit, or?
Right. Yeah, let's see. Let me, if I can go backwards. All right, see the handles? There's 4 handles on here. Good question. I mean, I wasn't involved with the mechanical aspects of it. The mechanical engineer is Bob. What's his last name? Bob. Gosh. And Bob was involved with Oscar Forty in the Orlando laboratory. And Bob's a really good mechanical engineer, so he's come up with this. So the idea is, yes, they would take this, and I'm trying to remember, what is the size of this, Bill?
Roughly
So
20 by 20.
20 by 20 by 10. So, you know, so yeah, the idea is that they're going to suit up for the EVA. It'll be a Russian EVA because technically this satellite is a Russian experiment. They'll take it through the airlock with them, and then once they step out on the other side, they're going to toss it away. How they're going to toss it, whether they're going to push it or swing it, I think the desire is they would like to have some spin on it. But I think what they're going to have to do is do some analysis, and they'll no doubt do a mock-up of this and then put it in the water tank and actually practice with it in the water tank, and then that'll go into the procedure of when it actually gets deployed next year. That's about the extent that I know it, so it'll be interesting to see what they come up with. Okay?
I noticed there was a fair amount of mechanical stuff there, and I wondered if you guys do any mechanical testing, vibration testing in particular. What occurred to me is usually with space vehicles, it's not enough for your stuff not to work. You don't want it to fall apart and trash the rest of the rocket or payload going up.
Well, true, and this is not going to go on the pointy end of a rocket. It's going to go into a nice cushioned, padded capsule. Not to say there's not vibration, but I don't think it's like the same amount of vibration when it's bolted to the top of a rocket. We are paying attention to vibration, and the way we do that is, of course, in the mechanical aspects of it, and we also do things like everything's Loctited down, everything's coated, and protective coverings that are put on things. So the mechanical aspect is paid attention to, but in obviously the launch aspect. But once it's off the progress, then all the vibration, we're fine. Of course, we want that to survive, the progress launch. Okay?
Steve, what's the estimated lifetime of this satellite?
Okay, good question. The putting the solar panels on there, the SuitSat 1 lasted 2 weeks because it was just batteries. So we wanted it to last a little bit longer, so the idea of putting the solar panels. SuitSat 1 was basically in orbit and burned up a little over 6 months from its deployment. So we would estimate, if everything goes well, that it would last, 4 to 5 months. And of course, once it gets closer and closer and it overheats, then obviously I would expect it to fail long before it burns up because of the heat. Okay? Let's see how we're doing here. I think it's time to bring up the next talker. Thank you very much.